Hello, we are B3 engineers. Thank you for having us today and allowing us to present our custom water system tailored to the needs of remote communities on the West Coast, which will provide sufficient, clean, and easily accessible potable water in a timely and cost-efficient manner.
Our project was to design an easily maintainable rainwater storage system that will collect, pump, clean, and store water for use throughout the year.
We are designing for a household for 2 people in a small remote community somewhere in BC. Though many areas in BC receive an ample amount of rainfall, the rainwater collection system design needs to be resilient against external factors.
During our decision-making process, we started by creating satisfaction curves, analyzing level of water consumption, and measuring flow rates. Near the end of the project, we developed system models and tested different attributes in order to choose all the components of our system.
Since this was obviously a model and cannot reflect the real world in terms of complexity and scope, a set of assumptions had to be made to give the calculations reasonable ground. The following numbers were used as baselines in all of the calculations and were kept constant throughout the modeling process. One weakness of our system is that we assumed emergency water shipped in could not be stored for later days of use.
We did not consider the cases where temperatures are so hot water evaporates from the storage tank, or freezing temperatures which will cause additional problems.
Our system will consist of the following major components. Rainwater catchment. We plan on using both sides of the roof for catchment. This doubles our catchment area, making in total 100 square meters. This doubles the amount of water collected and only costs an extra $350. The catchment tank is located beside the house. To disinfect the water, we decided to use the combination of UV disinfection and ozone as our means, where an alternative, as discussed later, was chlorination. The energy supply used in our system will be a diesel generator supplied with imported diesel, where the alternative was solar power.
We chose the diesel generator since the efficiency of the generator is greater than solar options. We chose not to use solar panels because they are hard to maintain and repair in a remote community, making the diesel generator a more resilient choice in this context.
When critically comparing to chlorination, ozone can treat wider variety of waterborne pathogens and won't have chance to give the water chemical taste or smell. The initial cost of ozone will be $4,000. The energy required to disinfect will be 2 megajoules per ozone, and the minimum dosing of the device is 50 milligrams times minutes per liter.
We decided to use Pump B, which uses 120 volts of AC power, and referring to the plot on screen, we believe it will have the optimal pressure versus flow rate relationship for a long-term water system out of the pump options given. We decided to use a 200 5N 1 micron filters and the UV system to filter. The addition of the 5 and 200 micron filter is cheap and worth the added maintenance filter costs. We decided to use 2 12-volt lead-acid batteries for our design, where the alternative would be to only use one, which greatly lowered satisfaction and reliability ratings. The water will be pumped to a storage tank that is located 6 meters in elevation above the catchment tank, 24 meters away from the house. We positioned it in this location so that the water would be able to be fed without a pump back to the house, all powered by gravity. The alternative design considered was to change the elevation of the tank to 8 meters above sea level and 5 meters from the house, which we didn't continue with as it significantly decreased on-demand flow rate.
The house and the collection systems are originally around sea level. The elevation of the water storage tank was considered as pressure increases with increased elevation. Consideration of accessibility for maintenance was considered in the placement of the storage tank.
After 5 years, we expect the total cost to be around $47,000, while only shipping and water would be $100,000.
From the weather station data, an average can be formed to estimate the system specifications, ensuring sufficient water supply. This is important considering climate change, since average rainfall will decrease and water consumption will slightly increase. To test the robustness of our system, we altered the order of months of weather data available and scaled the rainfall volume by historically abnormal rain seasons of plus or minus 8% and plus or minus 14%. We found that our system satisfaction dropped the most by 11% when the rainfall and weather data were at their most inclement settings.
Our system is designed to provide 570 liters of water to a household per day. This achieves general coverage for standard day-to-day consumptions of 550 to 650, aiming to supply satisfactory water quantities even when water usage is higher than normal. A medium to large storage tank will be used to adapt to the usage and water differentials over the course of multiple days to weeks between rainfall.
Our simulation satisfaction score is comprised of the criteria graph, namely consumption needs, relative cost, and environmental consciousness. Our system achieved a satisfaction score of 71.9%.
Our system design shows both positives and negatives regarding environmental impact.
We calculated and compared greenhouse gas emissions of the existing system and our proposed system. Based on the calculations, our system produces approximately 2,000 kilograms less of greenhouse gas emissions over 5 years compared to the current system. The stakeholder satisfaction we found was to be 19.42% higher.
According to the severity matrix and the frequency analysis, we discovered the ozone disinfection system and diesel generator will have a low impact on health and environment due to its low maintenance frequency.
We have designed an easily maintainable rainwater-based storage system that will collect, pump, clean, and store rainwater for use throughout the year. Our system will satisfy the case study's water consumption. The system is not only extremely cost-effective and costs a third of what it would be to ship in water, but is designed so that it will prosper in remote West Coast communities for a household of 2 people. Thank you for taking the time to listen to our presentation. We've been B3 engineers. Have a good day. And any questions, please ask us now.